We'll have a panel discussion on the subject of will position, navigation, and timing be the killer app for quantum sensors? Our panelists will be Airbus Quantum Technology Central Coordinator Dr. Jasper Simon Krauser, Sandbox General Manager Luca Ferrara, Infleqtion VP of Strategic Initiatives Dr. Max Perez, and our moderator will be Global Quantum Intelligence Chief Content Officer Doug Finke. So please welcome them to the stage.
Thank you. Yes. Well, good afternoon, everybody. So we're going to talk about quantum sensors and whether they're going to be a killer app. We're all attending this conference at the end of the day to see if we can do something useful with quantum technology and be able to make some money with it, as picture there. So we're going to talk a little bit. Okay. We're going to talk a little bit about how that might happen in the sensor world. Some people think that sensors may actually do it first before be able to be commercially useful before quantum computing. So let me start with Dr. Jasper, and maybe you can introduce yourself and just a little bit about who you are and what you do.
Yeah, thank you very much. So my name is Jasper Krauser. I'm the coordinator of the quantum activities at Airbus. We have started, I would say, as an end user of this technology quite some time ago, roughly 10 years ago, to look into the different pillars of quantum computing, communication, and sensing. And of course, sensing has a lot of applications in the aerospace domain where Airbus is active. And that's why we're, of course, excited about these technologies. But we also see in our activities the difficulties to get this running and to really bring it to commercial value. There's a lot of things to be done. And that's why I'm happy to be here and to discuss about that.
Very good. Okay, and Luca, maybe you can introduce yourself and what you do and who you are.
Sure. Hi, everybody. I'm Luca. I'm the general manager for our navigation team at SandboxAQ. We focus on quantum magnetometers used to deliver an alternative PNT solution that's based off of magnetic anomaly-based navigation. So that's what our team is currently working on. We work with folks like the U.S. Air Force and other aerospace majors, and we're developing that technology to be one of many solutions that's going to help address this looming threat to GNSS outages. So we know, unlike the previous discussion about when is Q-Day going to come with a quantum computer, you can pull up and see data that reflects that there's thousands of incidents already happening every day of GPS being spoofed and jammed. So the threat there is real, and like many on this panel, I'm here to help be one of the solutions.
Okay, very good. And finally, Max from Infleqtion. Why don't you go ahead?
Hi everybody. I'm Max Perez from Infleqtion. I'm the VP of Strategic Initiatives and acting GM of our Ticker Optical Atomic Clock portfolio. So it's pretty exciting to be here. We're essentially on the stage with potential customer and collaborators to attack the PNT problem head on. The specific thing we're doing at Infleqtion with respect to my work is developing next generation optical atomic clocks that provide the timing part of PNT. See if I can, there we go. The timing part is critical for a number of systems. It's the backbone of GNSS, GPS systems. It's also critical for communications and datacom systems throughout the world. Nothing happens without the timing part. In addition to the timing part, we also develop inertial sensing technologies that provide some of the positioning capabilities for PNT systems, as well as platforms for next generation RF transmission and reception.
Thanks. Okay, so there's been a number of proof of concepts and trial demonstrations. I'm going to go down the line here and ask each one of you which ones are some notable ones that your company has done. But even more important, do you have any applications right now that are using some form of quantum position navigation or timing in a what I would call a production mode where people are using it on an everyday basis. So why don't we start here with Jasper?
Okay, so we start with the, let's say, the system integrator. So Airbus is producing, probably best known for our aircraft. We're also building helicopters, satellites, military aircraft. So it's a broad portfolio, and there are many things where you can use quantum sensors. We are exploring also different applications. PNT is one of them. But for us, it's not yet in a, let's say, product state. So we are not including them in our products. All what we are doing so far is bringing them, let's say, from a, let's say, subsystem level into an aircraft for test purposes and working our way around how we can in the future integrate them really into a product. And that's a quite challenging task. So it's not a black box, which you just screw into your aircraft and it's working. There's a lot of integration efforts to be done. This is where we are at the moment.
Okay. Max?
So we operate on both sides of the fence. For example, we supply subsystems into system integrators like Airbus for integration in their much larger systems with respect to our clocks. And we also provide, as standalone capabilities, the frequency references that are required to demonstrate the applications that are critical for the future. So we work with early adopters, researchers in the field in order to figure out how to use these new capabilities for navigation applications, as well as straightforward communication and scientific applications. On the other side, we also supply our subsystems both in the lower TRL sensor side, as well as the higher TRL timing side to the aerospace industry for integration into larger platforms.
Now, do you have any customers that are what I would call in commercial production right now, or still in a POC stage versus POC stage?
So our particular timing products are in a pre-production capacity right now. Our customers haven't brought them to full production. They're exploring the use cases. They're applying them to test cases. And we're what we like to call a validation and verification stage. So that includes military customers, in terms of government customers, in terms it includes commercial customers. They're essentially figuring out if the technology is suitable for their needs and what the value proposition is when integrated into their systems. We have sold a number of these systems to commercial users in datacom, to scientific users who are exploring timing networks, as well as to government customers who are looking to validate them for much larger system-level deployments. But yes, it's entirely in a validation and verification stage, and we intend to go into full production next year, in which we'll be supplying the scientific customers with end-use products for smaller volume applications.
That's Nick. And Luca, maybe talk about some of the POCs that your company has done, or whether anyone's in production yet.
Yeah, I think in aerospace, when you reach production, is obviously partly you have to go through certain regulatory or certification channels in order to make sure that you're complying by what's industry standard. So quantum doesn't give you a free pass when it comes to that. It actually probably invites more scrutiny, right? So, and maybe rightly so. So I would say that we're on a path to production. I think we've identified the key parties that we'll need to work with and are working with those parties so that we can achieve certification. From the defense side, though, we're able to move faster. As far as POCs, this past summer, we were able to demonstrate for the first time, to our knowledge, a commercial system doing magnetic navigation in real time on a customer platform, where the pilot was looking at our magnetic navigation solution in real time and waypoint navigating using it, albeit in a constrained circumstance, not in operational theater. So that's something that we're excited about, but it's not the same thing as perhaps having pilots navigate on it every single day in production.
Yeah.
But it's an example of how you can show people value along the way, and have them visualize what the product is actually going to look, not quantum sensor, is going to look like in the hands of an operator. And so we're excited about that. And I think that there's more to come. But as far as production environments go, I think we must live within the confines of the aerospace industry. And so that's going to dictate our timelines.
Okay, very good. So when people talk about PNT in general, the first thing that comes to mind is GPS, something that augments or replaces GPS. And we'll talk about that in a few minutes. But I want to first delve a little bit into what are the other applications of a quantum sensor that are not navigation. And I think, maybe Max, you might have the most of the three, but why don't you start and tell us some of the other applications that you see your customers looking to use your stuff for.
Yeah, there's a really clear division between the commercial use case and the government use case with respect to clocks. The commercial use case, the highest volume use case is generally in datacom and telecom. That's a very price-sensitive, large volume application set, but in terms of commercial viability, it's the largest single market for time and frequency products. Optical atomic clocks, like the one we're developing, Ticker, represents a step function in the performance relative to the older technologies based on microwave technologies. And so we expect that this technology will gain immediate traction with respect to the highest performance part of the telecom and datacom industry, and then the adaptation will increase as it moves down to the lower performance, more price-sensitive parts of that segment. The real exciting place in datacom and telecom is in optical networks. Right now, most of the optical networks are along the backbone, but as they move further into the processing part of the systems, we expect that optical atomic clocks will become much more pervasive.
Okay. And then Luca, Jasper, do you have any other non-GPS type of applications that you guys are looking at right now?
Well, I think we're always evaluating. There's some interesting explorations we've done in areas such as mineral exploration. Can you use the sensor to better determine what's under the soil, right? We know that a lot of the rare earth metals and other materials that we need in order to go green in the future are rare, hard to find. There's a lot of companies that are trying to find better ways to source those materials. So could you use quantum sensors to better ascertain what assets are under the ground? I'm not sure, but it's an interesting question, and it's the kind of thing that I think perhaps is an example of where these sensors could play a role. That could be a killer app of sorts, perhaps.
Okay.
Yeah, on our side, we have, since we have a larger portfolio, we have looked also in a quite different ways how we can use quantum sensor, and PNT is really it's a very promising application with a lot of potential impact, but it's only one out of, let's say, really many. So in Airbus, what we do internally, we are clustering those applications, and we have 5 different areas where we see them and where we are exploring them. One, which is very interesting for us, it's maybe a bit specific, is inspection. So if you can use them as an inspection tool, it's obvious that for an aircraft that's for maintenance, etc., that's very interesting. And here quantum sensors are very interesting to their sensitivity. However, of course, it needs to be something which is handled by a maintenance engineer, right, or maintenance worker, which means it's not straightforward, direct, right away. But from the performance, it's very promising. We have one cluster which deals around observing effects around an aircraft. This can be done via, for example, enhanced LiDAR systems. So it's not really quantum sensing in a way that it's a completely new sensing setup, but you replace some of the components with quantum components and increase incrementally the performance of other sensing systems. We have one, metrology was already mentioned, has a lot of nice applications also in the defense area, for example. And we have also one, which maybe is worth highlighting, which is to use quantum sensors in space. So we have, for example, an activity where there's also in Europe, there's quite some effort to use a quantum sensor as a complement for a mission to observe the gravity field of the Earth in the future with a higher accuracy. So those systems are already out in space. They are very accurate, but you can make them even more accurate if you add on those quantum sensors. What all of those have in common that the quantum sensor is not really self-standing. So it's always only a small part of a larger sending system, and this makes it also complex. So it doesn't mean that once you have this brick, everything is fine and it's commercialized. There's still these adoption efforts to be done.
Okay. Okay, well, let's turn to navigation, something that either augments or replaces GPS. And, let's start with something that, was talked about a lot. And I'll ask you, Jasper, to also comment. Why do we need something to replace or augment GPS? Isn't GPS good enough?
I mean, GPS is great, right? Today, there are many of the applications we use. Everybody uses to come here to this event. You use GPS. When we think from an aerospace or let's say aircraft perspective, GPS is also used as one of the several navigation systems to do the navigation. So we have today, we have an extremely reliable navigation systems, which typically, I think Max points out, we have inertial measurements. We have different types of matching techniques which are already used today, and we have of course GPS. So all of these systems come together. If one of the system, for example, isn't working, let's say GPS is not working, this still means we have a reliable navigation system. But of course, we need to adjust over time. You might lose accuracy, so we need to adjust then the operations, for example, of this aircraft. And this is done all within a highly regulatory frame, so the flight management system is then adjusted. And of course, the airlines would be very happy to have a redundancy to GPS because it would improve their operational efficiency. So just to give you a commercial example. So that means it's definitely, I think, something which is very valuable for the aerospace sector. And so that's why we're also so happy to have these opportunities and to collaborate also in the ecosystem, because in the end, it's not really sure if we're going to use that, right? There's a lot of decision points to be taken, but I think it's very promising.
Okay. So Luca, I think you might deal a little bit with military type of applications. You think the military might have some special concerns about having something that backs up GPS?
So I think that there's a very compelling case on both sides. In commercial aviation, there's obviously a very high premium put on safety of flight. And there's, triple redundancies and all sorts of different things that are there because we care about safety of flight on the commercial side. So I don't want to discount that side either. But for sure, the use case that we think of and that we've validated for the defense is, well, I have a mission to complete, and not having GPS cannot be a reason for me to not complete that mission, is the desire. Versus, I want to be in a situation in which, should GPS jamming occur to me, that I can maintain safety for, not necessarily that's mission oriented, right? So it becomes more of a capability and less of a resiliency type of thing in broad strokes. Of course, there's nuances there. So I think that in general, there's certainly an appetite for many technologies for alternative PNT, because GPS, although the military has a better version of GPS than what we have commercially available, there's still this looming threat, if you read the strategy papers, about, well, what do we do on a day zero fight against a peer adversary if the satellites themselves are vulnerable? Because jamming and spoofing, there are countermeasures and there are techniques and procedures to deal with it degraded. There's a spectrum of degradation that you can deal with. But if it's a lights out situation, this is the kind of existential risk that strategists think about sometimes. And so when you think of it from that lens, there's going to be a perennial desire, I think, and we've seen it, to develop many technologies that basically take the target off of GPS's back, so that we can maybe stop having this conversation about what do we do if GPS is gone, because there's no reason to get rid of it. So from our perspective, magnetic navigation, fits one part in that, but like any of these technologies, they add the most value if they're differentiated and uncorrelated with one another. So if the GPS is out, that has little to no correlation on whether the magnetic signal is available or whether the inertial system is still running. That should have no impact, right? For its time and so on. And so the collective of these things is what we really should care about. And I think if you look at the strategy of the defense community in terms of the research groups, they're putting bets on all these things, right? And they should. And so we are part of that. But we have to be clear-eyed about just being part.
Okay. And Max, anything to add in terms of defense concerns with GPS?
I'll just say there's the other half of the problem. So GPS and GNSS systems provide very specifically positioning and navigation information, and that's assured by some alternative technologies, magnetic navigation, gravitational navigation, inertial navigation being options that come from quantum. The other part of the problem, though, is the communication systems. As the bandwidth goes up, most of the defense community relies on very, very high bandwidth communications between many, many disparate systems. Those are all synchronized by time. That time is currently provided by GPS. If you don't have access to GPS, those systems slowly become unlocked, and you start dropping bits. You start dropping comm systems. Providing assured timing, both locally and distributed timing networks, is going to provide a big part of the problem for when you don't have access to a GPS or GNSS system.
Okay.
Pretty good.
Let's turn a little bit to technology and how do you actually build these things? What are some of the basic technology to use? And I'll start again with Luca in terms of the sensors that you guys do. What technology do you use? Things like NV diamond or vapor cell or optical or whatever.
I like to say we're agnostic to that because we don't want to be in the business of producing the sensors.
Okay.
It's our belief that for our use case of navigation, the sensor is not the limiting factor anymore. It's been several years since that's been the case in our view. And so really it's about making the sensors better for commercial applications rather than more exquisite, let's say. So, we've got expertise in NV diamonds, we've got expertise on optically pumped magnetometers. There's always the classical magnetometers that are consistently, depending on the use case, may actually be good enough, right? I think, Jasper, you mentioned earlier, quantum systems sit among classical systems typically, right? The whole system is not typically quantum. So there's opportunities there to make use of advantages or advances that are happening in the classical side. All of which is to say that we're always in conversations with with magnetometer producers, and we have the expertise to evaluate and benchmark them for our use case. But it's not my belief that we need continued progress on the sensor for magnetic navigation to be possible. It's a whole host of other things that make the hair gray, but it's not that.
Okay. And Max, what technologies are you guys using right now?
So we focus on quantum atomic technologies at the basic level. So everything we do involves interacting an atom with a laser in order to both prepare the state of that particular atom and extract information from it. The reason why we do that is because that tends to be the way of getting to the highest performance part of the problem in the quickest and lowest size, weight, power, and cost way. So there are certainly other modalities, and they're valuable in their own right, but that's where we focus as a company. So, for example, at the heart of our atomic clocks is a little glass box. It holds a collection of atoms. We interact with those atoms with a laser beam, both to compare the state of those atoms and to extract the timing information. And then there's a closed loop with a resonator in order to perform a clock, to form a clock. We work with both cold and vapor-based systems for different applications. Generally, if it's a vapor-based system, we're targeting a lower cost in which we're trying to maximize the amount of signal from the collection of atoms. If we're working with a cold atom system, we're generally working with a higher performance system in which we're minimizing the amount of noise. So in terms of this conversation with PNT, our vapor-based systems are really, really great for our near-term optical atomic clocks, and our cold atom systems are really, really good to perform those to form those inertial sensing systems in which the noise has to be minimized in order to maximize the amount of time that the system can navigate before there's some drift.
Okay. And Jasper, you're an end user, so I don't think you develop the sensors themselves, but you evaluate them from companies like these. Do you have any favorites, or are you agnostic also?
We of course we are agnostic. I mean, that you have to be agnostic as end user. It's actually, if you say that, it's not really correct that we are not at all looking into the sensor themselves. So in particular for some applications where we know there is most likely no supply in the future. In particular, if you think about, let's say, a space mission where you develop a dedicated sensor, you have to fulfill all the requirements in space, giving, let's say, radiation, launch requirements, shocks, and autonomy for, I don't know, a few years. This is something where we have also developments internally. For the rest, it's correct. We are partnering. We have a range of partnerships also with navigation systems, I would say. So partners who work, let's say, on the have already an integrated system which we can use, but also on the sensor level itself. Because for us, it's actually interesting to understand, let's say, the full the performance at the different levels. Also to set up the architecture. So I mean, that's important. So it's not that you just put a sensor into your product. You need to have a developed architecture how you want to use them, and this is something where we as a system integrator need this type of knowledge as well. So that's why we are working broadly, I would say, with different partners, also with different technology. I mean, the most at the moment are essentially our Rydberg atoms, our cold atoms, and our NV centers. This turns out to be, for our, let's say, core favorite applications. Favorites, I don't have one, but what I can say, right now we are in an exploration stage, which means we do not really care about swap, so size, weight, and power. However, this is going to change in the future. When it comes to a program and when you want to integrate this, the size will play a role. And then, of course, some of these technology, in particular, for example, diamonds have a certain advantage, but they're also limited in a certain sense, right? So which means you need to really, to find the right sensor for the right application to also validate the commercial viability. And that's going to be quite a lot of work, right? So I think for some applications, it's likely we will not use the most advanced quantum sensors. Okay, we're already saying maybe we are even fine without a quantum sensor. And for some, we will definitely need very advanced system, maybe even ultra-cold atoms. So.
Yep. Okay. Well, you brought up SWAP. That's SWAP, size, weight, and power. So that is, of course, very important for all these applications. But let's start and talk about where we are today. So, Max, maybe you can tell us, just give us a physical description of the systems that you are offering to some of your customers. Is it like the size of a microwave oven? Is it the size of a rack pedal? Or is it a little chip? Or what's the physical size and weight?
Last things, absolutely. So, for example, we just sold delivery of a half a dozen of our 3U rack-mounted clocks to the Department of Defense. For validation and verification.
Okay.
So these are 19-inch rack, full rack, 3U systems, so about 3 pizza boxes tall. They're really targeted for indoor instrument level applications, but you can integrate them onto larger craft, both airframes and terrestrial craft. For use as a local frequency source in the event that you can't have access to that frequency source via GPS or another distribution method. That particular system has been picked up by Space Force and targeted for a 5-liter package, and we have direct line of sight of what we need to do with the technology and to get it down from about 30 liters in its rack-mounted size down to about 5 liters. And that's really focused on providing an upgrade path for the current frequency references that are used aboard GPS and alternative GPS systems. As a good example, what Space Force is interested in is deploying a resilient GPS network, which puts these systems on smaller platforms in order to have many more systems at a lower cost. And so SWAP plays into that, especially in the space game where the launch costs are the significant part of the overall cost of the system. Our 3rd generation system beyond the 5-liter system is a sub-liter system, which performs full integration of the photonics and the atomics to produce a board level device. And that's really targeting the commercial application in which the cost has to be absolutely minimized. The ability to manufacture at volume is maximized. And it has to be integrated with board-level electronics. So you can think of in 3 generations. I don't think we're unique there. I think most quantum technology developers have a similar path where you have an assembled product to start. You have a partially integrated product that's the the second generation, and then you have a fully integrated product for the highest volume markets. And this is a path that has been demonstrated from previous successful technologies. A really good example in the time and frequency industry is the CSAC, or the chip scale atomic clock, where you go from larger demonstrations down to fully integrated products over the long term.
Okay. And Luca, some of the stuff that you are working on right now, give us an idea of the size and weight.
Yeah. So the pizza box example is a good one. Yeah. So, few pizza boxes, depends, thin crust or not.
Okay.
Deep dish style. But I think there's an important difference for magnetic navigation, which is that the sensors themselves are, the size of a watch. I mean, they're small, right? You can hold one in your hand. But it's the array of those sensors and how much space they require to get the information and the number of them, which is the real lever arm for us in terms of the cumulative swap. So if we encapsulate everything into one box, and then, so the demo that I mentioned earlier, the whole system is put into a box around the size of a suitcase, a checked bag, let's say. That checked bag goes onto the airplane and then is hooked into a normal outlet. So there's not a terrific amount of power that it requires, right? And then it operates from there. But most of what's in there is air. And it's there mainly to get spatial separation between the sensors that we have in that box. The reason I mention this is to illustrate the fact that the swap as such is not so relevant if we think of the integrated solution as if you were to integrate these sensors into an airframe as an example, they wouldn't need to be shrunk much more. The problem is that, for the challenge, let's say, is to actually get to the point of integrating to an airplane is a long journey. But we don't need the swap to necessarily make orders of magnitude change. And for us, I would just say that we have systems that are rack mounted as well, but it's the same thing, which is that even that is just a partial way towards this fully integrated solution. So echoing a lot of what you said.
And Jasper, are those sizes that these guys are talking about small enough to fit inside an Airbus airplane?
Of course not. No, but what I mean, right now, so an aircraft, of course, provides a lot of room for those sending systems. In particular, I would say now, and this is really important for exploration, in understanding how we can integrate this, how we use this, and how we also bring then really the value for a product. I wouldn't say that the swap is driving, right? Because let's say if we do test flights, you imagine a big aircraft, an A350, and you do a test flight with that, then of course you wouldn't care if that's a washing machine or if it's 3 racks, right? You have enough space. Of course, if you integrate this, then really then the size plays a role. But I would rather come from the other side. If we have a need, and if we see this provides benefit to the customer, let's again take the example, the airliner can operate the aircraft more efficiently. Then it's the question, is the airline, is it worth the market value and is it worth to include this extra system on board? And swap is only one of the many criteria we have. So that's why I would say I wouldn't worry too much of this swap at the moment, in particular for commercial aircraft. When we come to defense application, I think you would agree it's different. But let's say it's more important to really be sure we have an added value coming from this technology to have this in the future.
Okay. So, we talked, the title of this session is a killer app, and really killer app means you're probably going to want to implement it in some consumer level product. So rather than selling maybe thousands of airplanes, maybe millions of automobiles. And I'll start with Max first. Do you ever see that something like a quantum navigation sensor would be cheap enough and small enough to be used in an automobile?
Yeah, but I think, so for example, the clocks that we're thinking about, it's probably going to be used in a different way than you might expect. So one of the most exciting things you can do with high-performance frequency references is start to synchronize, say, the onboard radar systems in autonomous vehicles, so that you can get improved precision for true level 5 autonomy. And I think it's those type of applications that might end up being the killer app for quantum technologies. So use of the improved performance that's enabled through quantum for applications that are a little bit of a right turn to what we're staring at right now. So to answer your question just slightly more fully, we expect straightforward deployments of these high-value, high-performance technologies in aerospace and defense at the current sizes that Airbus isn't too worried about driving down the swap out of for the highest performance, highest value applications. But then once they're out there and they're validated and people start to use them, they'll start to say, oh, these things can be used in a variety of other applications that are even more higher volume, but are a little bit of a left turn from what we're looking at right now. So there's the sky's the limit in terms of the number of applications that might provide a killer app. Even if we're kind of driving towards the clearest applications that are apparent today.
Okay. And Luca, how about?
I like everything you said. I mean, that's okay. Yeah, that's absolutely. Yeah. What can I add to that? I don't know. I'm sure that we're not predicting the killer app. I think that's probably safe. But probably by the time it's the killer app, no one will remember it's quantum or internet.
Yeah.
This kind of a conference will, we'll remember, but like to people who are using it, will be like,
right.
Isn't it just like a computer thing?
Of course.
Yeah. Just what is that? So hopefully we all succeed to that extent where people don't even realize it's a quantum technology at all or appreciate the difference. So there's probably that. But I do think that the timing aspect, when you think about all the things that rely on timing, I mean, it seems like a ripe area for something to eventually hit the consumer. Because, like, as an example, for magnetic navigation, there's already companies which are using your cell phone magnetometers to map spaces like this and then provide better analytics to event planners about where people spent their time, because they don't need the level of performance that we need.
Yeah.
So in a sense, it's already hit the consumer. I don't know if a quantum sensor really changes their experience much. It's just not the same.
And I don't know if the question's relevant to you, Jasper. I'm not sure Airbus makes any consumer products right now. Maybe in the future.
Defense, well, if you say an aircraft is quite far away from that. I mean, I would be quite optimistic that the problem is if you have a new technology and you have it on a certain level, and then we see this progress, right? And this is amazing how this has developed over the past. If you extrapolate this, we will find those applications, I'm quite sure. So if it's in the consumer industry, I don't know. Maybe there is something that's a bit more specific, and we have to learn that. What I like very much what you were saying, we don't really know yet the killer app, and maybe it's a bit too early, and it's maybe also not the point, right? The point is that we have a very exciting avenue, and once we are there, we will see. And I think this is what we can learn from other technologies, that in the end, you cannot predict exactly what you're using this for.
That's very, very true.